All right, well, hello everyone. I'll be presenting some implicitly parallel analysis tools that we've been developing as part of the DOE-sponsored SciDec4 program together with the NOvA experiment. So as you know, high-energy physics experiments collect massive amounts of data, which is a feature of our high-intensity beams. The problem can quickly become intractable, though, as event structure complication rises and as we develop detector technologies with finer resolutions, like in the case of the liquid argon time projection chamber. The first step of many of these analyses performed by these experiments is to filter through the data to extract the features that they want to analyze. Since each event can be processed independently, this task is easily made parallel. And so far in this conference, we've heard from a number of frameworks that are designed to do just this. I'll present our analysis ecosystem, which leverages high-speed interconnect and data storage and delivery capabilities of high-performance computing platforms. And I'll also show an example analysis from the NOvA neutrino oscillation experiment. And although what I'll show you is in the context of neutrino physics, the framework is designed to be experiment and domain agnostic in order to support all types of columnar data analysis. So first off, the foundation of our analysis ecosystem is HDF5, which allows us to take advantage of the native and highly scalable parallel I/O and compression features of the format, as well as the highly optimized MPI implementations provided at HPC facilities. HDF5 also boasts a large investment from industry players, and so as the format grows, we're able to sort of piggyback off of those developments. So we've designed a schema for efficient columnar analyses in HDF5. Here, the deeply nested n tuples that we're used to are flattened into separate tables. And then the elements of those n tuples within each table are stored and directly read in columns. In the language of HDF5, these are groups and data sets respectively. And so here, each row in each table are indexed by event number and some additional run information in order to associate event features across tables and to support irregular table sizes within a single file or within a single analysis. For example, each of these T-tree branches that I have in the left here would become a separate HDF5 group. And the leaves of those branches become data sets within the group or columns within those tables. Then using the run information, we can associate the neutrino energy like I have here with some information in, say, the spill group, and that's held in a separate table. HDF5 I/O is performed by chunk and supports partial reading of data sets as they're needed. This allows us to analyze files of arbitrary scale without adding overhead to many parallel processes reading smaller portions of the data. So we've looked at how we can benefit from concatenating many of our HDF5 files into smaller and smaller number of larger files using some software that was developed by collaborators at Northwestern University. Here we demonstrate scaling event selection time as we concatenate an entire NOvA Monte Carlo dataset into fewer and fewer files. We find that a single monolithic file provides the most flexibility in terms of analysis configuration with a consistent 10 times speed up compared to similar analysis on the equivalent individual files that make up the monolith. It was made using only 985 CPU hours on the NERSC Core system. With that, it compressed 3 terabytes of uncompressed data down to about 280 gigabytes, which at that point is suitable for laptop analyses as well. We've also developed a Python-based event selection framework that we call PandAna to sift through this HDF5 organization. PandAna implements implicit parallelism using the event indexing that I mentioned earlier in order to distribute the workload among different MPI processes running a single job, all without the user needing to intervene to code any of that up. This leverages HDF5's parallel chunk-based I/O, and again can handle irregular group sizes. Users in this framework write PandAna cuts in vars, like in these examples they have in the bottom left or bottom right. These cuts and vars accept PandAna tables, which essentially is a proxy for HDF5 groups. And they return, the tables return pandas data frames as a result from reading the data. And so here, by requesting this rec.vertex.elastic group, the data is read and returned into a real pandas data frame, which at that point, the user can perform arbitrary operations on the data, pandas or otherwise. Also, these operations can be as simple as one-liners like I have in the neutrino energy variable down at the bottom, but can also be something much more complicated like this fiducial volume cut. Some potential improvements in this framework that can be made are reducing the number of redundant and superfluous event indexing information that's read in order to match the events across different groups. But also general improvements in the overall data flow using something like an abstract syntax tree. We're also developing an implicitly parallel histogram package that we call Llama, just to stick with the animal theme. It wraps boost histogram for performance and feeds from the pandas data frames returned by PandAna. Reduction operations here are performed lazily for common histogram operations based on the arithmetic properties of those operations, which you can see illustrated in this flowchart. Here, each process has its own copy of histograms H1 and H2. And when the user wants to sum these into H3, the results aren't collected from all the processes until they're needed. They need the aggregate result at serialization time. Additionally, these histograms implement the unified histogram interface for easy plotting with other tools like MPLHEP. So to show a complete workflow, I present here an analysis of realistic scale, which is a measurement of the electron antineutrino charged current cross-section in the NOVA near detector. We analyzed multiple samples of Monte Carlo, which in total contains almost 200 million slices in time and space. These are held in about 600 gigabytes of 4 of those monolithic HDF5 files. The number of unique HDF5 groups and data sets accessed within each file are 16 and 54 respectively, just to give you a sense of the complication or the complexity of this analysis. And then finally, using NERSC's new Perlmutter system, we achieved near perfect scaling with a total processing time on the order of minutes, which really enables us to do real-time exploration of the data at this scale. So this example illustrates, again, an implicitly parallel Python analysis workflow in the context of neutrino experiments. But as I said earlier, these tools are well suited for any columnar data analysis. So if any of this interests you, please feel free to watch the repos that I linked in this talk or to reach out to the team. Thanks.
Okay, thanks very much for this nice talk. So we have a little bit of time and we have one question on Slido. Are local analyses on laptops common in your field? I have rarely dealt with more than 1 gigabyte of files locally before moving elsewhere, but this particular question asker is coming from Atlas.
Okay, yeah, they're not so common in our field just because the data sets that we have are typically pretty massive. And so this sort of, enables a completely new workflow that might be completely contained on your laptop. But as of now, it's not super common in neutrino physics, as far as I know.
Okay. Okay, and so it doesn't seem like we have any other questions on Slido. I'll go ahead and ask. So for your Llama library on slide 6 that you said is basically like an extension of boost histogram. Is the work that you're doing there to make it to add the parallelization, is that something that, excuse me, is that something that is big enough deviation from what's currently done in Boost histogram that it needs to kind of stay its own library or stay as its own library, or is this something that you think there might be able to be contributions back towards the upstream library?
Right. So I'm not super familiar with the inner workings of Boost. I know it's a pretty large library, but yeah, these operations are relatively simple, I would say. And so it would be interesting to explore adding that into Boost. But for the purpose of this study or workflow, this is we sort of decided just to build upon that for now.
Yeah. Okay, great.